So Al has asked me to talk a little bit about a computer that I designed 40 plus years ago. My name is Hugh Anderson, and I've recently returned to New Zealand. I was working overseas in Fiji and Singapore for quite a bit of the last 25 years. In 1976, I think, I was living in the UK, and I ended up, I think the following year, or I ended up seeing a popular electronics article about a computer you could build for $90, and I built this computer, and it kind of started my interest in computing. Over the next few years I did all sorts of things, extended the computer. I think I went up to a blinding, the particular computer had 256 bytes.
Not even a kilobyte?
No, not even a kilobyte. And I extended it to 512 bytes.
Whoa,
oh, blinding. But anyway, I ended up back in New Zealand in 77, I think, and maybe 78, I'm not sure. And I designed my own computer using the same technology. So this was a computer based on the RCA CDP 1802, which was a CMOS microprocessor. So it could have a clock speed of 0. You could just switch the clock off and it would just stay where it was. It was very cool. And I did my first embedded system that I sold to someone for, I think, $50 to do something, was based on an 1802 and ran off a tiny battery. But anyway, when I came back to New Zealand, I decided I would try to be an entrepreneur and sell these things. I tried to sell the kits and how to build them of components, and I was unsuccessful at that. And then I ran into a guy called Jim Coyle, who had a company called Kit Parts, and he encouraged me to design a proper printed circuit board for it, which I did do, and that was the HUG1802. I think we started selling it in 1978. And we eventually sold about 100 of them, and so that's the sort of history of this computer. And if you want to have a look down here, you will see there is a working one, semi-working computer. This was it had a hex keypad. It had a couple of buttons. As you can see, it has a loudspeaker, and but the amazing thing about this for the day was it had an output display, and so if you see on the wall there, I'm actually projecting it with this little projector just to show the video display you would get with it. This computer has 1 kilobyte of memory, of RAM. It has a kilobyte EEPROM. And you could certainly write little programs and run them on it. Had a cassette tape interface, video out, sound, and so on. And the software in it, there was also an interpreter in it for a language called Chip 8, and so it interpreted Chip 8 program. When you reset it, you could simple monitor, you could look at memory locations. For instance, at the moment I'm looking at memory location 0600 and it's 15. I can change it to 12, and then I can change the next memory location and so on. So it had a very simple way of loading in programs and running them. And you could run machine code programs, and you could run Chip 8 programs. So well, that's the computer.
There was the Kim 1, which had come out probably, I don't know, around 1976, I want to say, somewhere in that region.
Yeah.
This looks quite similar to a Kim 1 style machine. So what were the differences between this and the Kim 1?
Well, the KIM-1, as I remember, it was a 6502 based computer. This one is a different microprocessor, 1802.
Yeah.
And the company that had manufactured it, RCA, they made the chips back in the day, they had made it so that you needed very few actual integrated circuits to make a working computer. So this one, I think, the smallest one with video had only 7 integrated circuits, and it was cheaper. You know, when these were sold, they were sold in New Zealand for $120, $130, and I think a KIM-1 would have cost twice that, maybe 3 times that,
Right,
a lot
right.
more. But yeah, of course there were many, many more KIM-1s than there were HUG1802s. So what this does is it's running it under emulation. For reset, you can inspect memory. So that's first byte is in the ROM. That's F8, 04, B2, and so on. Because they're in the ROM, you can't change them. If we reset the computer and look somewhere else and go there, we can change this to 32 and so on, right? So this is the way in which you can operate it. So what I'll do is I'll load up, let's try chess first. So we'll go load.
And you're loading this into memory address 0600, is that right?
Yes, and so that's loaded in, and now if I'll just reset the computer, so that's now at 0600, and if I key, I think it's 8, yeah, okay, so that's midway through a game that my brother Bruce was playing 40 years ago. If I go C, it'll clear it back to starting positions.
Hey, I just want to pause the video for just a moment. I want to tell you about something really important, right? Okay, imagine that I could tell you about a place that you could go to that would give you 3 benefits, potentially even 4. So those benefits are really cool. Number 1, no more ads, right? So if you went onto this website, you could get no more ads in all of the videos, right? So no more of those YouTube ads. Okay, number 2 would be your name in the credits of every single video that I made from that point onwards. And number 3 would be a full feature-length video, right? So the videos that you see on YouTube, some of them are just the short versions. You could have the long versions and all the geeky goodness in those videos. So those 3 benefits would cost you only $3. That's great value, right? You've got to say, every single video that I make, it costs me a lot of time, money, sweat and toil, and you could get all of that good stuff for just $3. And if you're a higher tier subscriber, then you could help shape the content on the channel. All of that, plus you get a community where we can all talk and be part of something. I've got a Discord server, I've got original content which is completely separate on this. Well, what is it called? How do you get to it? You go to Patreon. Patreon.com/Al's Geek Club, and as I say, it only costs from just $3 little bucks. Patreon.com/Al's Geek Lab. Don't forget, on these videos as well, I really appreciate it, really helps out with everything. If you subscribe to the channel, press the like button, remember to set all of the notifications on, and also if you can drop some comments, I love to see your comments. Look, that's all. I really appreciate your support. I love the fact that you're viewing my content. I hope that you enjoy it so much that you want to come over and be a person who helps out at patreon.com/Al's Geek Lab. Right, back to the video.
And then we can ask the computer to make a move. It actually uses a book to make its move, and it does the Duco piano, however that's pronounced. So it'll be quite quick to make its first move, and it just pushes a pawn. So if we were to push the corresponding pawn, it's from 6, row 6, 1, 0, 1, 2, 3, 6, 3 to 4, 3. So I'll go 6, 3, 4, 3, and then F, and that will move that pawn. Right, so the pawn has, so they're both done pawn to king 4. By the way, that blindingly fast screen redraw you just saw is the actual native speed of the assembly language writing the bytes to the screen.
Right, so it doesn't, for that machine, it doesn't get any faster.
No, that's as fast as it gets.
Yeah.
Although there is a trick, because the screen is just put up there by DMA, you could allocate another screen memory and write to that and then just swap
like a
the
screen
DMA
buffer.
pointer. Yeah.
Yeah.
And in fact, there were games that used that.
Right.
If we go D again for the computer to do its move, it's very quick, and this is because it knows a particular opening, and as long as we follow the opening, it'll be quick. But if, for instance, if we did something unexpected, like that's not part of the piano opening, so if we went 7, 5 to 6, 5, we just push a pawn. 7, 5, 6, 5. The blinding power. Sorry, I did 7 for. Oh, that shows it moved. What a bishop! Okay. So it went wrong there. But anyway, now if we ask the computer to make a move, it will actually take a long time. It'll take about a minute to think about it.
Really, as long as that? Wow.
Yeah.
Okay.
I don't think we're going to wait a minute.
And so when you're running with, obviously this Jess here has a specific command list that the move parameters.
Yes.
But when you've got basic, does it just take fairly normal, like 10 print hello, all that sort of stuff? You can give it sort of normal commands.
Okay, well look, let's not worry about waiting for that. I'll just do a reset and we'll load up basic. Right. Load, so now we'll try loading basic. Basic 1.bin. Loaded OC100. Okay. And now I think I go reset, and then go 6, I think, to run a machine language. Yes. So that did just write out HUG basic there.
I can just about see it there. Yeah.
So let's just reset it a few times until it gets down to the bottom of the screen. Okay.
Right, here we go.
So there we have HUG basic. Now, actually, I remembered I need to clear out where it's going to store the programs. So let me just quickly do that. Okay. So now, so we're in a mode where we can list out the existing program, and I just put in 0 for line 0. So if we go 1, it should write a 0. Right. I'll now delete that line, and I'll put in a new line number. So good grief, do I remember this? Okay, so it's line number 10. So I've put in 10. I think I can put in a space now. And then we're going to do this program, plot rand go to 10. So 85 is the code. So you had to know these codes. So it's got the codes at the back.
Right.
36, 2C, 3. So hang on, I've made a mistake.
It's not as simple as just typing the words itself. You have to remember codes.
Yes.
Yeah.
8, 5, 3, 6, 2C, 3, 6. Yeah. So that's plot rand, and then we can go. Line 1, 4 will be 20, and now it'll be go to EB 31. So there's our program. If I exit out here and list it, we go 1. Yeah, that's our program.
Looks good.
And so now exit out again, and now if I press 0, it'll run that program.
Pixels on the display. So what is the resolution of the actual display?
So it's 64 pixels across 8 bytes, 64 dots across 8 bytes, and 48 vertically to give a aspect ratio that's about right. But the hardware can actually do 64 by 192, but programmatically we make it look like that. It's interesting, these are supposed to be random, and you can see the lines going like that because the random number generator in it is in the interrupt routine. It adds 1 to a number every time it's in an interrupt.
Oh, right, okay. Not the random. The entropy of this machine is not high.
No, I don't think that RAND will win any awards. Yeah.
Oh, that's cool.
But so that's an example of basic running under emulation.
Will we zoom in and have a look at the machine, and you can maybe talk about the components, maybe?
Sure.
Is that right?
Okay. This is the board. So this was the microprocessor chip. That is an RCA CDP 1802. They're kind of weird processors. They had 16 registers. The one I have over there is silicon on sapphire, and these are in space, and I believe to this day they're in space. Because this is radiation hardened, right?
Because of the sapphire.
Because of the sapphire,
right?
Yeah. And so these are just the ordinary. This is one of the ordinary black ones, but the one over there is, very expensive one. That's the real one over there. That's silicon on sapphire, I believe.
Cool.
Yeah. And so the processor was not fast compared, similar, bit slower than a 6502, but it had some blindingly fast things. So, for instance, when you wanted to, say, jump to a subroutine, though it had a go sub, you could also just change program counters. And when an interrupt occurred, that's exactly what it did. It just changed program counters. It didn't save away where you were. Like normally when you get an interrupt, it saves registers and jumps to it. But that's not what the 1802 did. And the joke at the time, of course, was that this was for use in space and for weaponry and nuclear weapons. When it responds to an interrupt, it doesn't need to return from that interrupt. It gets the interrupt that says explode.
And that's it. Explodes. One time.
Yeah, I don't know if that was the reason for it, but in some ways it looked a little bit like IBM mainframe instruction sets with these 16 registers, so the chip next to it is another RCA chip. This is a 1864 PAL color display chip, and they put everything in there that would produce video, and all you actually needed was this chip and that chip and a clock and maybe a ROM, and you could put video up. It was intended for games, I think. Now I'd been doing development with 8085s, I think, and certainly with 8080s, and so I was and 6800s and 6803s, I think, at that time, and I used a 6821 PIA, peripheral interface adapter, to interface with the keyboard. So this is a plug for the keyboard. So we have the processor, we have the video display. It also had a oscillator, a programmable oscillator on it, and it makes the tone. So you can play music, you can play tones quite easily. You just do an output instruction to this and it will just play this tone for you for as long as you want. And then the I/O through this 6821, a Motorola product. In this original kit set, it had a 2708 1K by 8 EEPROM, and so that the EEPROM and EEPROMs in both of these computers are still working. So they are 43 years along from when they were programmed, and they've had a little sticky thing on the, they're erasable with ultraviolet light.
Yeah.
And they have a little sticky on top, and they've lasted for Yes,
Yeah,
we'll go top of the
just
top.
a piece of tape over the top of them.
Yeah, and
Amazing.
they appear to have exactly what's supposed to be in them. Here, this is embarrassing to show this, but I will. This, for instance, is the source code of the monitor.
Oh wow! There you go, written in pencil or pen. Yeah.
Written in pen with corrections and things, and you know, by this time I'd been using an 1802. I didn't need no assembler or anything. I could just write the binary code out, and that's what I did. And I still have these original source codes of the monitor and of a basic interpreter somewhere, partial. So this is partially my basic interpreter. And not only that, I have an 8K source code listening there that's complete of fourth for a different, it's something that wouldn't run on this computer, and I no longer have a computer that it would run on. So I just, you know, things were a little different back in those days. One thing that happened with this is in 1980, I believe, the person selling it, that's Jim Coyle of Kit Parts, he sold the design or the idea to the Australian magazine ETI, Electronics Today International, and they did a kit set called the ETI 660, which is essentially the same computer. They did a new printed circuit board, a better one. I think, like mine, they laid it out with tape the way you did in the old days, instead of with a computer, you know, CAD design. But they made a few improvements. One of them was became a single power supply. This thing requires +5, -5 volts, and +12 volts, whereas the ETI 660 could just run off +5 volts. The only difference was the EEPROM. So mine was, you know, 3 or 4 years older, used a 2708 1K/8 EEPROM, which needed 3 power supplies. The ETI 660 used 2516, which had only a single power supply. They also improved the colour circuitry, so it provides colour video out, but I had, as a cost-saving measure, I had got rid of a delay line, a 390 nanosecond chrominance delay line, which gave good colour, and my colour was essentially had a little inductor and capacitor circuit to do the same thing very, very badly, but it was cheaper. And so they put the chrominance delay line back in, and that colour was better than mine. But apart from that, it's the same ROM, it's the same memory map, it's the same circuit, apart from power supply and chrominance delay line. Yep.
So you said there was probably about 100 of them sold. Is that right?
I think so. In New Zealand, I think they sold about 100, and then the ETI 660 came out, and Kit Parts, the company that had been selling the HUG, then started selling that kit as well, and I think they sold more of that than they did of mine. So this is 1980, and by this time it was being published by ETI. Oh, it looks like I got a commission of $4 each. Yeah.
Big money. Very cool. Thank you so much for your time. I really enjoyed seeing this. And it's not many chances you get in New Zealand, especially, to speak to somebody who actually created a computer, especially when computers were computers, you know.
Yeah.
But to see somebody that is the author of the machine and actually, you know, go through the parts, that's just wonderful. So thank you so much, Hugh.
Good. Okay.
Awesome.
Well, it's a pleasure.
Cheers.